So in section 3.1.3, we have the same Laplace's equation, but in two dimensions. So let's go back and copy Laplace's equation as we proved it earlier, which is this part over here. Copy it and paste it right down here. So now we know it's in two dimensions. Let's take x and y. Therefore, z is gone, and it's always equals to 0. So now we have to use partial differentiation, and now it becomes a little bit harder because we cannot actually solve this. As you can see, there will be infinite solution to this equation, because we could take, for example, mx plus b, and it will be a solution to our equation. But also my plus b will be a solution to our equation, or mx plus my plus b, for example, or something really different. mx plus ky plus b will be also a solution. So as you can see, we can now define one single solution to this whole thing. But how can we then solve this part? Well, let me start erasing this. And I want you to imagine a very specific scenario. As the book mentions, imagine you have, first of all, the axis, so in x, y, and z axis, but on the z axis, we're going to put the potential V. Okay. And then we put a box on top of this. This means that we're going to have something like this. Very perfect. I want you to understand it very well. Okay. And the potential, for example, this point here goes all the way up here. And the potential over on the z-axis goes up here. The potential over here goes up here. So now we need to connect these points, and we can connect it by some simple curves. Something like this. Of course, here, sorry, we'll go, let's say, up here. Okay, so now one thing that you can notice is that you can now imagine a circle of radius r, capital R, at this point. Okay, and then you draw the circle going up and actually finding the potential that is on this circle. So let's call this circle, let's make the circle like this. Now, to make it more clear that it's on a 3D surface, let's make it like the book does. As you can see, there are some ups and downs. In the center is this point right here. So, in the one dimension, we proved that at the center, we're going to have the average of the points on the sides. But if you think about this, we have points on the side everywhere. I'm making a different color, actually. So, it's easier to spot. Okay, so one point here and one point here will have the average at the center. Another point here, another point here will have the average at the center. Another point here, another point here will have the average at the center. Another point here, another point here will have an average at the center. So the whole thing will actually solve because the average of the points all around will be the point at the center. And we can show this by saying that the voltage, the potential average, is equals to, well, 1 over the area of our circle, which is going to be equals to 2 pi r times the integral, the circle, of the voltage times the distance covered. As the book mentions, this is also something that is used by the computers to solve the this kind of equation. It's called method of relaxation. But anyway, as you can see, all these points will have an average that is equal to the central point, to the point at the exact center of our circle. Because if we imagine, for example, a line in one dimension going up like this, we would see that the average is right here. If we imagine another point, a line that goes up like this, let's say the average point of these 2 points in blue is the point at the center. So as you can see, it works in one dimension. It works in 2 dimensions just as well as in one dimension.